Welcome. This is a new lesson about Taylor series. So in this lesson, we will learn about series expansion and function approximation. So in usually there are like a lot of mathematical expansion. For example, Fourier series. So Fourier series, if you have like a periodic function, you can approximate this function through a series of sine and cosine function, for example. Taylor series, that's a very interesting one because it tells you like if you have a function, you can approximate this function by a series of the derivative of this function. That's how I will approximate the function. Probably this is not very clear now, but once we uh, uh, get into it, then it will become more clearer. But so in this lesson, basically you'll understand the fundamental of series expansion, like what is a series expansion, like including Taylor series and special case of this Taylor series, which is Mac Maclaurin series. And then you will become familiar with the role of series expansion in analytical and numerical solution. Because like, why do we want to do this? Like, I mean, is this just like, are we doing this just for fun or this is something important? Actually, this is something extremely important, not just important, because we will see that sometimes analytical solution, you cannot have a closed form solution. A closed form solution, like let's say f of x is equal to x squared, like f of partial x is equal to 2x. That's called the closed form solution. Some equation, like when you get to partial differential equation, you cannot do something like this. And in that case, you can do like a numerical solution. And for a numerical solution, you need like Taylor series. But before doing a numerical solution, you can do analytical solution with something called infinite series. And for that, for example, you use Maclaurin series. And I will show you example like from like I'll show you example like a pumping well where you are pumping water out and you have a differential equation. This differential equation you cannot solve it with like this closed form solution, and then you have to use analytical solution with Maclaurin series, for example. And then when we get to the next module about modeling, I will show you how this Taylor series is like a central concept in many of these numerical solutions, and how you have like a differential equation that you cannot solve analytically either with a closed form or infinite series, and then how you can solve it numerically with Taylor series. And that's why this is not just something we are doing it for fun or for FE exam. Yes, you'll also see it in FE exam, but this is one of the central concepts. But like enough talking, and let's just start getting to learn it piece by piece. Like if you don't understand much of what I said now, that's fine. You will, by the end of this lesson, you will understand a little more. And when we get to a differential equation, and I will like remind you of what we did here, then you have a better understanding. And then when we get to the modeling module, and I will remind you of what we did here, you have a better and better and better understanding. And I know for some of you this is overwhelming, especially if you are like in construction management, for example, and you're saying, "Oh, why are we learning this?" Yeah, and I told you at the beginning of the semester, why are you learning this? Because that's basically to get a degree in engineering, you need to know all these basics and fundamentals. Yeah, but I don't know if this is makes sense or not, or this is like the optimum for you or not. But I mean, that's a different issue. Yeah. But let's just focus. This is an important topic and actually a cool topic. So even if you're not interested in these things, uh, you will really like these. Just it's just like some cool things. Yeah. So let's say like I have a function. Yeah, like that's like my function like f of x. Yeah, and I want to approximate this function around a point. Yeah. So I want to up around the point. Let's say like f of x I. Yeah, around the point to obtain like f of around a point with step size. Let's say I will have like step size h. So that's like my step size. That is like x I plus 1. So this is minus x I. Yeah, so this is xi plus 1. So one step, this is basically one step size. So I could be like equal to 0, I is equal to 1, I is equal to two. So here, for example, like from one step, so that basically how you define a step size. Yeah. Uh, so now I will tell. So this is my function, and I will tell you, okay, what is f of x I plus one? Like my next point. So I have a point here, yeah, and I'm telling you what is like I know the value. Like let's say I know the value of my function here, but I don't know the value. So that is like x. Okay, so that's like let's say here that is xi, and here is xi plus one. I don't know this guy here. So basically, I am I am I can tell you like the value of this guy here is equal to the value of this guy here, like like the value here is equal to this value. Yeah. So if I told you the value here is equal to this value, this means what? This means that I will just extend this. That would be like a straight line without any curve. Yeah, just a straight line. But let me tell you, the value here would be equal to the value here. So that would be just straight line without any curve. But let me make it a little bit more interesting. I will tell you like the value here. Remember, like a Taylor series, like I approximate a function at a point by its derivative. I will tell you this is like the first derivative of like this guy over like 1, okay, to the power h. That's like my step size. So what did I do here? So it's not only like a strength here, like this is I'm adding a slope and then I'm multiplying. So here I'm adding a slope. So this is like slope and I'm multiplying it by this here. So this is my h, because remember h is xi plus 1 minus xi. That's h. Yeah. So here I'm adding a slope. So let's say like this is a slope. Yeah. So like this is the point here, and I'm assuming that there is a slope here, and then I just like multiply it by that distance. Yeah. So what did I do here? I just like, so instead of having like a point here, I'm adding a slope. I will have a point here. Okay. So that is how I approximated this guy. Yeah. Now, can I do better? Yeah, I can increase my series. I can say, why I don't say that this is like the second derivative, yeah, over this guy times h squared. So what did I do here? I didn't add just the slope. I added like some kind of like curvature here. So this is not just like straight line here. This will make it more like this, like more like I'm adding like a curvature here. That's like, because remember, like the first derivative is slope, the second derivative is curvature, the third derivative that would be like a twisting or something like this. Yeah. So I can say like the third derivative of I, okay, and h to the power 3. And I could just go on, yeah, and until like whichever I need to stop at. So I can basically say like plus, yeah, n here xi over n hn plus rn, whatever is reminder. So basically, the value of this guy here, yeah, is just this approximation. So if I have no closed form solution here, where like no way like here, basically I can just like know this guy by knowing this guy, and through like this approximation. So basically I approximated my function at a point, which is this point, through the derivative of this function. That's basically what the Taylor series is. Again, let me tell you, I have a function f of x, yeah? I approximated this function at a point here through knowing the derivative of this function. So basically this is just what you see here, yeah? So this this function at a point is equal to the function plus the derivative of this function, and until like whatever is here, that could be like until infinity, or if you don't go to infinity, that would be like the remaining error or truncation, yeah. Okay, so example of Taylor series. Let's do an example, yeah. So use 0 to, okay, one thing I didn't tell you, this is called like, yeah, this is important. This is called like 0 order approximation. This is like first order approximation. So if I only consider these two terms, that's like first order approximation. If I consider like these three terms, that's called like the second order approximation. If I consider like three terms, that's the third order approximation. So here, like this is telling you, now see, this is to the power 4, and I will show you this now. I'm telling you, use 0 to fourth order Taylor series expansion to approximate the function from x0 with a step size h1 and predicts the function value at xi where this is equal to 1. Okay, so basically like what we are giving here so we are giving here basically like x0 is at 0 and xi plus 1, that's 1. Yeah, and so the step size basically, so that's like, so that's the step size. So the step size is xi plus 1 minus xi. So that is like 1 minus 0, that's 0. So that's why you get this step size. Okay. So how can we do something like this? So remember, you just bring your equation. Let's just bring our equation here. Let's just, uh, it's asking me for only to go up till the fourth order approximation. So I can remove these guys. So here, this is 0 order, first order, second order. Let's do two more. So Control C. Oops. Control V. Control V. So basically that is up to now to the fourth order approximation. I just need to change this like guy here. That would be like 3. Yeah, that would be like the power of 3. I change this guy here, 1, 2, 3, 4. That would be to the power of 4, and that would be. So now, if I now let me explain again what is going on here. So this is my function, yeah. So this is like the function that I have, and I want to approximate this function at x is equal to 1. Okay, and I know like xi is giving, so xi that's like is 0 and xi plus 1 that is equal to 1. So I wanted to approximate it here, and I know my function and I know it like at xi. So how to do this? Basically you need to find like these derivatives. So you find like the derivative of the first function, the derivative, like the second derivative of the function, the third derivative of the function, and so on. So like the first derivative of the function, for example, like you know how to do this, yeah? So you, so that would be like minus 0.4, yeah, x to the power 3 minus 0.45 x to the power 2 minus 1x minus 0.25, and that's something like this. You know, like how to do this, yeah? So that would be like minus 1.2 x to the power 2, here minus 0.9x minus 1, yeah? That is like the third derivative would be minus 2.4x minus 0.9. The fourth derivative of x, that would be minus 2.4. Yeah, that's basic. And then you know h, yeah, and then you just like substitute here. And then you evaluate your function for x is equal to, so basically like you substitute, like what you do here, you find like f at xi. So xi, that is like 0. So you find like your first derivative at 0, yeah? And then you evaluate like your second derivative like at 0 also, and you evaluate like your third derivative at 0 and like your fourth derivative at 0. Okay, so you do this. Let's see how we are doing in time. I don't want to take so long. Okay, so if you did this, let me just show you like the solution here. Yeah, so basically that is what we have here. Let's look at the zero order approximation. So the zero order approximation basically that will so that is the zero order approximation. It will be just like I have like 0 here. I substitute this here, so this will go away, this will go away, this is 0, this 0, then I get 1.2. So what does this mean? This is just exactly what I showed you previously. I mean, I have a graph, so I plotted for you. So let's just, so this is the zero order approximation. Yeah. What is the first order approximation? So the first order approximation is like the zero order approximation plus the derivative of this guy to 1, the factorial of 1. So the derivative of this guy, this is just what we saw here. We substitute 0, then you got something that looks like this. We know the exact solution, by the way, because I can just in this function, like so in this function, if I put like x is equal to 1, like f of 1, so the exact solution would be 0.2. So you see here, like my first order approximation, I am far away from the exact solution, the true solution. Yeah. In my second order approximation, I'm like a little bit closer to the exact solution, but still like far away. When I included like the third term, yeah, like this third term here, which would be basically like the first derivative, second derivative, plus like the first approximation term, the second approximation term, and like the third approximation term, which is the third derivative, then I'm getting something closer to this. When I get to the third order approximation, which will include like the third derivative, which is this guy here, then I will get something very, now I'm approaching to this. When I go to the fourth order approximation, like considering, let me show you, like, considering basically, oops, when I go to the fourth order approximation, going up to the fourth derivative, then I get like the exact solution. And why did I get the exact solution with the fourth order approximation? Because this is like a fourth order polynomial, and with the fourth order polynomial, if you fourth order like term, you will get like to like the exact solution. So let me show you this, like I plotted this for you and I can show it to you. Okay, so basically, so okay, so this is my function. Yeah, so you see like this is my function, so this is my true solution. So at x equal to 0, yeah, I have f of x is equal to 1.2. Yeah, this is like at x equal to 0. Now I want to find my function at, so at x I, f, which is like f of 0, I have like 1.2. Now I want to approximate this function to find my fxi plus 1, which is like f of 1. And I know the true solution for this is 0.2. Yeah. But with my first approximation, what did I do? So basically my first approximation, all what I'm saying is, that's my first approximation, like is that this guy will, I will just like move this guy here. So like f of x1 is equal to f of x0. Basically like this guy would be equal to this guy. So all I did, I just like moved like this point here. with the first order approximation, you see this guy here, I assume that now there is a slope. So now I started to move this guy down because now I assume that like I have this guy here plus I have this like slope here. So now I added the slope. So you see this looks more like slope. Now, if I looked at, so this is the zero order. So this is the zero order approximation. This is the first order approximation. This is like the second order approximation. If I look at the second order approximation, I started to have some curving. So this is just like sloping here. Now I have started to have some curving because remember, like the first order, this has to do with the slope. This has to do with curving. This is the second order. Now this guy is like the third order approximation. And with this third order approximation, I started to have a little bit of twisting. So this point, see, is like not just like sloping or curving, but like you start to see some twisting here. And with the first order approximation, I just get like, I'm refining these twisting and I got just exactly to the right point. So at x is equal to 1, my f of x is equal to 0.2, which as I got here. So if I substituted, sorry, this is 1 here. If I substituted 1 here, I'll get 0.2. If I did this Taylor series expansion up to the fourth order, I'll get the same thing. So you see how cool this is? Like how could I approximate a function by its derivative? So basically like this guy, like basically like what I'm saying here is that like this guy, like this function f of x, yeah? So, here, let me leave it. Let's see if I can did I do it here? Yeah, I did here. Let me just copy this guy. I didn't have this guy. Let me have this guy here. Yeah. So I'm saying here, I can approximate like this guy at a point by this guy. So basically, this guy at like x is equal I equal to 1 is equal to this guy. Okay. Let's do an example. Let's see how we are doing in time. So not bad. Okay, let's do an example, and maybe with an example like it will become clearer. So here, let's see what we have here. A ball height is given below by the below function. Approximate the ball height at t equal to 2 using a Taylor series expansion around t1, which is equal to 0, and compare with the exact value. So okay, so we can easily do this because, okay, so what is h, or what is like xi plus 1, that is equal to 3. What is like xi, that is equal to 0. What is like h, that is equal to 3 minus 0, yeah? And now, what is the true solution? Because I want to know the true solution. So the true solution, basically, I want to find f of x I plus 1. So that is like f of 3. So that would be minus 5, 3 to the power 2 plus 23 plus 1. And if I did this guy, the exact solution is just like substituted here, you will get something like 16. Yeah, so that's the exact solution. So I just wanted to get the exact solution by just substituting here, so that I will know. By looking at this, I know that up to the second degree approximation would be sufficient because this is the second degree function. So up to the second degree approximation would be sufficient. What does this mean? This means that I might not, so I need like this guys, the zero order, the first order, and the second order. That's all I need, yeah? Okay, what does this mean? So I mean, I can say like f prime of t, that is equal minus 10t plus 20, and f the second derivative of this guy is equal minus 10. Yeah, so that's basically all what I need here. Yeah, so what is the approximate solution? So the approximate solution, that is f of xi minus 1, like f of at like 3, that is like f of x at 0. So basically I substitute like 0 here, so t, so that will go away, that will go away, so I will get like plus 1 here. Sorry, I get like plus 1 here. The first derivative, what is the first derivative for 0? Like, so xi is equal to 0, so that is 0. Yeah, so I will get like 20, yeah, divided by 1 times h. What is h? That is like 3. Yeah, plus what is the second term? So that is my guy here, so that's like minus 10 over this guy here, times 3 to the power 2. So if I did this guy here, what do I get here? So from this guy here, I get 1. From this guy here, I get 60. Yeah. From this guy here, I get like minus 40. No, not minus 40, sorry. Yeah. So like from this guy here, this is 4. So I got, and this is 9. So this is, I got minus 10 times 9 over 4. Yeah, that's like what I got here. So if you, this is basically what, and this is plus 1. So what do I get from, this is, yeah, this is correct. So what do I get from here? So from this guy, I can get rid of this guy. I can get like a 5 here, and then this like minus 45 over 2, yeah, plus 60 plus 1. So this is would be, did I do something correct here? Okay, let's see what I'm doing here. Let me do it again. Doesn't look correct. So this is correct, yeah. This is correct. This is correct here. So let's just do this again. So this is 1. This is plus 60. Yeah, plus 60, and this is this is 9. 9 times 10. This is like minus. Okay, I got it. Minus 90 over 2. So I think I did the mistake here. So minus 90 over 2. So this is, I get like 60. I got here like minus 45. So this guy minus this guy, that will give me 16. Exactly, yeah, what I had here. So I had like an yeah, arithmetic mistake here. So that's like I got like the exact same answer, 16. Okay. So I approximated like this function by like its derivative. That's the key insight. So the key insight here, Taylor series perfectly approximates the function when the expansion order equal or exceeds the order of the polynomial. So here my expansion order is like I am up to the second order and the order of the polynomial is the second. So that's the key insight. Any additional term beyond the degree of the function in zero, and this will result like in non-truncation error. If I only approximated this guy like up till here, that will you will not get this one. So you'll miss this guy and you will get something very off like 61. Yeah. So you'll get uh, some truncation error. So basically that is the main take home from here. Let's see, this is like your homework problem. Again, it's very similar problem. I don't want to like, so here basically like that's approximate a pole at the height like t is equal with the series at t0. So you know like your xi is equal to 0, xi plus 1 that's equal to 2, your h is equal to 2 here. What else do we have? Yeah, and then this is up to degree 3, so this means I have to do like 3 of these guys like to get it correct. So if I went up to the third order, which means I need one more of these guys. Yeah, so one more of these guys, that would be like something like this here. So I will have one more of these guys as to the power of 3. That is 3. So I mean similar to what we did before, and you always know that you start these guys by finding like your first derivative, which should be easy. That's like 3 plus 6t, for example. Yeah, and then you'll find like your second derivative, that would be like 6t plus 6, and then you'll find like your third derivative, which should be like 6. Yeah, that's a constant. And then you just like evaluate, like you need to find this, like, so f of xi, yeah, for this guy. So that's like f of x 0. So you substitute 0 here, and then you get like, so if I substitute it, this is 0, this is 0, then I will get 1. And then you substitute here the same, like if, let me just do this, like that's your xi, yeah. So that's like your xi here, that's like your 0, yeah. So you got like 1, you substitute this here, you get like a number, you substitute this here, you substitute this here, you'll get another number, you substitute in your equation, and then you know your age, then you can approximate, you can find like this guy, yeah. And before you find this guy, just find the exact solution. So that's the easiest thing. So just plug in t over 2 here, like f of like 2 here, and that will give you the exact solution. And then compare what you get from your approximation with the exact solution, and they should match if you did everything correct. And that's how you can get the full mark in this homework problem. Okay, let's just move to one last topic. I promised you to not keep any week more than 2.5 hours, so I think I'm about to reach my 2.5 hour limit for this week. So let's just wrap this up quickly. So just something cool here. So if xi is equal to 0 in Taylor series, this is known as Maclaurin series. So what does this mean? So let's say I have like my h is equal to xi plus 1 minus xi, yeah, and this is my function. So for example, yeah, so this is what we already know, there's nothing new here. So for example, find the Maclaurin series of ex. So here I can say like my exi plus 1, that's equal to x, yeah, any value, yeah. But my exi, that is equal to 0, because that's the definition of the Maclaurin series, like this guy is equal to 0. So what will be h here? So h here will be equal to x, yeah, that will be my h. So let's just apply this here. So my function is my f of x is equal to ex. My first derivative, remember the first derivative of ex, that's the same as ex. The second derivative of of x, that's the same like ax. So that's like my first derivative, my second derivative, and so on. This is my x. So basically, like I just substitute this here. So my like just I'm substituting here. So that's like my f of x is equal to my f of x at 0. So basically, I'm evaluating this function at 0, like f of x at 0. So that is like e to the power 0. E to the power 0, that will give me 1. So my f of x, so that is like my first term here. That would be, let me write it a little bit down. My f of x here, my f of x is equal to my f of x like 0. That would be 1. And then like the first derivative over this guy, over this guy. So the first derivative, that's again like what? F partial of like 0. So that would be e to the power 0, that's 1. So like my first derivative, my second derivative, my derivative n, like the power 0, all of them would be equal to 1. Okay, so now let's just put all this information together and see what we will get. Yeah. So f of x, my x is equal to 1, that's x. So my f of x is equal to this guy, my original function to the power of 0, that's equal to 1, plus my first derivative is 1 over this guy, time h is equal to x, yeah, time x. Then plus my second derivative, that's again 1, all of them are 1, divided by this guy, and then my h, that would be like x squared. And let's do here the third term. Yeah, so the third term, again, that would be my third derivative, that's like 1 over 3 of this guy, and 3 of this guy. I can do all this all the way to like 1 over n, yeah, x to the power n. Okay, wow, what did I get here? So let's see, can I like simplify this a little bit? So let me just do some simplification. So this guy here, I can just like express this guy here as x to the power 0, because x to the power 0 is 1. And then I could just put here 0, the factorial of 0. For your information, the factorial of 0 is 1. Yeah, so that's the factorial of 0. Plus x square, sorry, plus x to the 1 factorial plus x squared to the 2 factorial. Wow! And then all the way down here. What does this mean? This means that f of x is equal to the summation of x, the power n, the factorial of n, from n equal to 0 to n equal to infinity. Wow! I mean, isn't this amazing? What does this mean? So my f of x is e to the power x, which means that e to the power x, you know, I can approximate it by this guy. That is how I can approximate e to the power x. I mean, why this is important? Like, why do we care to approximate e to the power x to make it like this? Because we know already how to evaluate this. We don't need to approximate it. Actually, this turns out to be very important, and I will show you when we get to differential equation. I will show you some partial differential equations that you cannot solve with closed form solution, and then you have to use this infinite series to find some form of analytical solutions. They are called like infinite series solution, and then you can get an answer, and you don't have to use any numerical method. So let's wait until this part, but for now, that's all like you need to know. The take-home message is the take, like I gave you this homework problem because the only way to learn this thing is to solve them. Like you can listen to this video 10 times, you're not gonna understand it unless you actually start doing it by yourself. That's how you're gonna understand it. The key take-home is that is series expansion is that I could approximate a function Taylor series that approximate a function through its derivative, for example. Other expansion could include like Fourier. I could approximate a periodic function through series of sine and cosine function, and so on. But here, this is very important because once we get to numerical method, you will see how Taylor series is a key concept, and once we get to infinite series solution, you will see how this is very useful. Okay, so that's all for this lesson, and